Let us continue alkali metals. In the alkali metals, we will see about peroxides. We will see about peroxides. Peroxides general formula. Peroxides formula O2 2 minus. This alkali metal peroxides are colorless in pure form. Alkali metal peroxides are colorless in pure form. But in the presence of trace of superoxide, it has fairly slightly yellow color. So alkali metal peroxides are colorless in pure, but a trace of superoxide is there means then it will show slight yellow color. Then peroxides are diamagnetic. Then reaction of peroxides will see. Peroxides react with water. Now we will take alkali metal peroxides. It is reacting with water to give what in the sense. This peroxide is having oxidation number -1. That -1 becoming 0. -1 becoming 0. That means undergoing oxidation. And another -1 becoming -2. That means OH minus, alkali metal ion. So peroxides react with water. In this -1 oxidation number becomes 0. That is oxidation. Another oxygen -1 becomes -2. That is reduction. That means it goes for disproportionation with water. So alkali metal peroxide with water gives alkali metal hydroxide and oxygen gas. Then this peroxide purifies air. It purifies atmospheric air. How it is purifying atmospheric air, that we will see. Now we'll take sodium peroxide, Na2O2. It will take atmospheric moisture and becomes sodium hydroxide and oxygen. This sodium hydroxide takes carbon dioxide and becomes a sodium carbonate. Sodium carbonate and water. Let us see the overall reaction. Now first we will balance this equation. Here 2 times sodium hydroxide, okay, hydrogen is 2, oxygen is 4, therefore oxygen is 4 is there. So we will do one thing, here off we will make. Oxygen is 1, here 2, 3, here also 3, okay, hydrogen is 2, correct, sodium is 2, okay, it is balanced. Next we will balance this one. Here sodium is 2 times, therefore here we will keep 2. Then hydrogen is 2, oxygen is 4, okay, balanced. Now we will see the net equation. Overall reaction we will see. Sodium peroxide we will write. 2 times sodium hydroxide get cancelled. Water get cancelled. Carbon dioxide we will write. Sodium carbonate and what? Oxygen. So sodium peroxide converts carbon dioxide into oxygen, we can say. The sodium peroxide converting carbon dioxide into oxygen. Therefore, we are saying sodium peroxide is used as a purifying atmospheric air. This peroxide used for purifying atmospheric air, you can say. Then we know that peroxide acts as oxidizing agent as well as reducing agent. In that oxidizing agent, it is powerful oxidizing agent when compared to reducing agent. It is better oxidizing agent, but poor reducing agent we have discussed. Then we will go for superoxide. Superoxide is a yellow in color or orange in color. Superoxide shows yellow color or orange color. Superoxide is having one unpaired electron. Therefore, superoxide is a paramagnetic. Whereas peroxide is not having unpaired electron, therefore peroxide is a diamagnetic. Then superoxide on dissolving in water, how the reaction takes place, that we'll see. Now we will take alkali metal superoxide. This we will dissolve in water. We are dissolving that one in water. What we are getting, that means this -1 here, this oxidation number is -1/2. Oxidation number is -1/2. This -1/2 becoming 0. 0 oxidation number. Then this -1/2 becoming -2. This -1/2 becoming -1. -1. This -1/2 becoming -1. So for two oxygens, minus of becomes 0. Other two oxygens, minus of becomes a -1. Therefore, we will take 2 times. Then we will write a metal hydroxide. We will write, for which water we will take 2 times. This we will write H plus OH minus. H plus goes to here, OH minus comes to here. This we will write 2 times. So superoxide with water gives oxygen, hydrogen peroxide and metal hydroxide. This hydrogen peroxide on decomposition gives oxygen and water. So next we will see about alkali metal hydroxides. We will go for alkali metal hydroxides. These alkali metal hydroxides are also called caustic alkalis. Caustic alkalis. Alkali metal hydroxides are also called caustic alkalis, we can say. Caustic in the sense corrosive. Alkali metal hydroxides, another name is what means caustic alkalis. Caustic in the sense corrosive. That means if you handle sodium hydroxide with hand, the fingers will become what in the sense in fingers we can see holes will be there, because it is corrosive. It is corrosive, therefore we are saying caustic, we are saying. So we can say alkali metal hydroxides are caustic alkalis. Why it is caustic alkalis? It is corrosive to skin. Another one is sodium hydroxide solution will be placed in glass bottles in the lab. Sometimes if you see the solution, sodium hydroxide solution will be outside the glass vessel. In the glass vessel we will store sodium hydroxide solution. What will happen in the sense sodium hydroxide automatically comes out from the glass bottle. Why? Because it is corrosive with glass. It is corrosive, therefore what will happen in the sense holes will be made in the glass vessel, then sodium hydroxide comes out from the glass vessel. So because of corrosive action over glass vessel, over the skin, it is called caustic. These alkali metal hydroxides are called caustic alkalis. So that we are calling sodium hydroxide as a caustic soda. Sodium hydroxide we are calling as a caustic soda. Potassium hydroxide we are calling as a caustic potash. Caustic potash. So sodium hydroxide we are saying caustic soda. Potassium hydroxide we are saying caustic potash. Sorry. What about solubility in water? Alkali metal hydroxides are quite soluble in water. Down the group, how the solubility will be there? Down the group. Now we will take alkali metal hydroxides, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Alkali metal hydroxides we have taken. Down the group if we go, size of alkali metal ion increases, ionic nature increases, so solubility in water increases, tendency to donate OH minus increases. Therefore, basic strength increases. Okay. So, this alkali metal hydroxides down the group behaves like this. Then, how the thermal stability will be there down the group? How the thermal stability will be there, that we will see. Down the group, thermal stability of alkali metal hydroxides, what will happen? How the thermal stability will be there for alkali metal hydroxides? Means alkali metal hydroxides are having strong ionic compound, more ionic nature is there, so it is not decomposing easily. We can say. On strong heating, it decomposes to give what? Alkali metal hydroxide on strong heating gives alkali metal oxide and water. So regarding alkali metal hydroxides, what are the points we have discussed? We will conclude it. One is alkali metal hydroxides are caustic alkalis. Why? Because it is corrosive over skin as well as glass. Next, sodium hydroxide we are calling as caustic soda, potassium hydroxide we are calling as caustic potash. Then alkali metal hydroxides are quite soluble in water. Down the group, size of alkali metal ion increases, so ionic nature increases, so solubility increases, dissociation extent increases, so concentration of hydroxide ion increases, so basic strength increases. Then alkali metal hydroxides are thermally stable, therefore on strong heating it decomposes to give alkali metal oxide and water. Then reaction with nitrogen we will see. Reaction with nitrogen. Lithium on heating with nitrogen gives lithium nitride. For lithium nitride, cation is Li plus, anion is N3 minus. Lithium nitride. Other alkali metals, sodium, potassium, rubidium, cesium, do not react with the nitrogen. No reaction. Among the alkali metals, lithium alone reacting with the nitrogen to give lithium nitride. Other alkali metals, sodium, potassium, rubidium, cesium, do not react with the nitrogen. Therefore, lithium alone forms nitride. Okay. Now, lithium nitride. On heating to high temperature, it decomposes to give lithium and nitrogen. Then lithium nitride undergo hydrolysis. To give what? This N3 minus takes H plus from water and becomes ammonia. Ammonia is a weak base. Its conjugate is N3 minus. Therefore, it is weak. So, it undergoes hydrolysis. So, lithium takes a remaining part of water, that is hydroxide, and becomes a lithium hydroxide. Okay. So we'll keep 3 here, here also 3. So lithium nitride on hydrolysis gives lithium hydroxide and ammonia. Lithium nitride at high temperature decomposes to give lithium and nitrogen. Then reaction with hydrogen gas, H2 gas, that we'll see. Reaction with hydrogen gas. Alkali metals react with the hydrogen around 673 Kelvin to give alkali metal hydride. But lithium gives hydride at 1073 Kelvin. Lithium gives hydride at 1073 Kelvin. Lithium gives hydride at 1073 Kelvin. Rest of the alkali metals gives hydride at 673 Kelvin. Then alkali metal hydrides we will treat with water. We will take alkali metal hydride plus water. What we will get, that we will see. This alkali metal hydride we will write alkali metal ion and H minus. Water we will write H plus OH minus. This H minus and H plus becomes hydrogen gas. Alkali metal ion takes this hydroxide and becomes alkali metal hydroxide. Alkali metal hydrides react with water vigorously and gives a hydrogen gas. Then alkali metal hydrides are thermally stable. Down the group, what happens to the thermal stability? That we'll see. Down the group thermal stability, what happens for alkali metal hydrides? Now we'll take lithium hydride, sodium hydride. Here Li plus H minus, Na plus H minus. Lithium Li plus size is small. Na plus size is high. So lithium plus nucleus attracting H minus electron cloud strongly. Strong attraction. Na plus nucleus attracting H minus electron cloud weakly. Attraction is less. So Li plus nucleus attracting H minus electron cloud strongly. Na plus nucleus attracting H minus electron cloud weakly. Here strong attraction is possible, here weak attraction is possible. Therefore, H minus electron cloud is strongly shared between Li plus and H minus. So sharing is higher extent. Here sharing is lower extent. Therefore, this stability is high. This stability is high. This stability is low. Therefore, we can say down the group thermal stability decreases. Thermal stability decreases for alkali metal hydrides. So that we can say thermal stability lithium hydride greater than sodium hydride, greater than potassium hydride, greater than rubidium hydride, greater than cesium hydride. So alkali metal hydrides thermal stability we have said like this. Next reaction with the water we'll see. How does alkali metals react with water? That we'll see. Alkali metals, as soon as dropped in water, it will react vigorously with water. So alkali metal with water gives what? That we'll see. Alkali metal is giving electron and becoming alkali metal ion. Water we will write like this. Now this electron is taken by hydrogen, this bond is shifting, therefore it becomes hydroxide. This metal ion and hydroxide becomes metal hydroxide. This hydrogen loses electron here, gains electron here and becomes hydrogen atom. Hydrogen atom combines with another hydrogen atom and becomes hydrogen gas. So alkali metals react with water to give alkali metal hydroxide and hydrogen gas. How this reaction will be there? Lithium reacts normally. Whereas other alkali metals, sodium, potassium, rubidium, cesium, react vigorously with water. Lithium reacts normally with water. whereas other alkali metals reacting vigorously with water. Why is it so? For that, when alkali metal is added into water, what will happen? What is the reaction takes place? That means this alkali metal has to convert into liquid, has to convert into gas, has to convert into ion, and has to go for hydration. Now, this lithium metal melting point is high. Other metals melting point is low. Therefore, it is not melting easily. It is melting easily. Why it is not melting easily? In the sense, it is not getting sufficient energy for melting. It is getting insufficient energy. So that it is not melting easily. Therefore, rate of reaction of lithium with water is low. Whereas other alkali metals get sufficient energy, therefore easily they are melting, therefore they are going for reaction vigorously with water. Then alkali metals react with proton donors. Alkali metals react with proton donors. How that reaction possible, we'll see. We'll take alcohol. We will add alkali metal. This alkali metal give electron and become Na plus. That electron, this electron is taken by this hydrogen, this bond is shifting. Therefore, we will get RO minus. This oxygen gains the bond, therefore gets a negative charge. And to neutralize the negative charge, Na plus. This hydrogen loses the electron left side, gains the electron right side, therefore becomes hydrogen gas. So, alcohol react with alkali metal to give alkoxide and hydrogen gas. Then we will take sodium. Gaseous ammonia we will take. Gaseous ammonia. How the reaction takes place here, that we will see. Sodium becomes Na plus by giving electron. Ammonia we can write like this. Ammonia we are writing in this way. Now this electron is taken by hydrogen, this bond is shifting. This bond is shifting to N. Therefore, this is becoming what we will see. This becomes hydrogen gas. Hydrogen gas, it becomes what you see, NH2. Already one lone pair is there. This bond pair becomes lone pair. Therefore, two lone pairs. Therefore, negative charge. To neutralize negative charge, Na plus is there. Na plus. Therefore, we are getting NaNH2, sodamide. We are calling this as sodamide. So, alkali metals react with what in the sense alcohols. This gaseous ammonia, then it is reacting with terminal alkynes. It is reacting with the terminal alkynes. Now I will take alkyne. I have taken like this. This is called terminal alkyne, we can say. Terminal alkyne. Why? Because triple bond present at terminal position. Now we will add alkali metal. Now alkali metal gives electron and become alkali metal ion. This electron is taken by this hydrogen. This bond is shifting to this side. Therefore, we are getting R, C, triple bond C. This bond pair becomes a lone pair now, and carbon gets a negative charge. Then Na plus is there to neutralize negative charge, and we are getting hydrogen gas. So this alkyne becomes alkinide. Alkinide and hydrogen gas is subtype. This is terminal alkyne only react with the sodium. Alkali metals. So alkali metals react with the proton donors like alcohol, gases, ammonia, alkynes, water, etc. Then alkali metals we are not exposing to atmospheric air because it is quite reactive with atmospheric air. Therefore, alkali metals are stored in kerosene, but lithium is stored in paraffin wax because lithium is floating over kerosene. Then we will see reaction with halogens. Reaction with halogens, we will see halogen, fluorine, chlorine, bromine, iodine, that halogens we will see. Alkali metals react with halogens vigorously to give alkali metal halide. To give alkali metal halide. These alkali metal halides are ionic compounds. These are colorless crystalline solids. These are ionic compound. Alkali metal halides are ionic compound, and these are colorless crystalline solids. We can say colorless crystalline solids. Down the group of alkali metal halides, how the standard enthalpy of formation will be there, that we'll see. Standard enthalpy of formation down the group, how it will be there. Now we will take a metal fluorides, then metal chlorides, alkali metal bromides, alkali metal iodides. Alkali metal iodides. Now lithium. Lithium with fluorine becomes lithium fluoride. For lithium fluoride, delta H naught F, delta H naught F is how much in the sense 612 kilojoule per mole. Lithium chloride minus 398, lithium bromide minus 350, lithium iodide minus 271. Next we will take a sodium. We will take for sodium fluoride minus 569, sodium chloride minus 400, sodium bromide minus 360, sodium iodide minus 288. Next, potassium fluoride minus 563, potassium chloride minus 428, potassium bromide minus 392, potassium iodide minus 328. Next, we'll see rubidium. Rubidium fluoride minus 599, rubidium fluoride, rubidium chloride minus 423, rubidium bromide minus 389, rubidium iodide minus 329. Next we will see cesium. We will take cesium fluoride minus 531, cesium chloride minus 424, cesium bromide minus 395, cesium iodide minus 337. That means standard enthalpy of formation of all the alkali metal halides are exothermic. Standard enthalpy of formation of all the alkali metal halides are exothermic. Okay. Now now we will take lithium. How the standard enthalpy of formation is there? Fluoride more negative, more exothermic. Chloride less exothermic. Bromide still less exothermic. Iodide still less exothermic. Therefore, how the order of negative delta FH naught is there for particular metal? For particular metal, fluoride greater than chloride greater than bromide greater than iodide. Like this is there. So now we will see stability. We will see. Therefore, exothermic nature is more means stability will be more here. Therefore, how the stability order will be there? Stability order will be F minus greater than Cl minus greater than Br minus greater than I minus for particular metal, particular alkali metal. Then how the melting and boiling point will be there? The melting and boiling point will be same in this order only. Then alkali metal halides are quite soluble in water. Now, among the alkali metal halides, lithium fluoride solubility is low. Among the alkali metal halides, lithium fluoride solubility is low. What is the reason? And cesium iodide solubility is low. Why is it so? Cesium iodide solubility is low. What is the reason? That we'll see. Solubility is based on two factors. One is lattice enthalpy, another one is hydration enthalpy. Solubility is based on two factors. One is lattice enthalpy, another one is hydration enthalpy. Based on these two factors only, that means a cumulative effect determines solubility. So what is the cumulative effect? What is the cumulative effect? That we will see. Now we will take sodium chloride solid. How sodium chloride solid will be there? On dissolving in water, it will become what? On dissolving in water, it will become what? Sodium chloride solid consists of ions Na plus and Cl minus ions. In the lattice, Na plus and Cl minus ions will be arranged like this. In the lattice, Na plus ions and Cl minus ions will be arranged in this manner, in a three-dimensional. Now we are adding water. What water does means water comes near to this. In water, water acts as a dipole, so positive charge here, positive negative charge here. So between them attraction is possible. Due to attraction, Cl minus detaches from sodium chloride and Cl minus goes to solution as Cl minus aqueous. That means hydrated Cl minus. Now here see, and similarly water molecule comes here. Here partial negative, here partial positive. Here attraction is there. Due to attraction, sodium ion detaches from the crystal and goes to solution as hydrated sodium ion. So here two process possible. One is this Na plus goes to solution by breaking attraction with Cl minus. This Na plus goes to solution by breaking attraction with the Cl minus ions. So for breaking the attraction, energy is required. Here Cl minus goes to solution after breaking the attraction from neighbors of Na plus. So Cl minus breaks this attraction and goes to solution. So breaking this attraction and goes to solution, no, breaking this attraction. So to break this attraction, how much energy is required? That is called lattice enthalpy. That means lattice enthalpy means you have to take 1 mole of crystal. In the 1 mole of crystal, you have to break like this attraction completely. For that, how much energy is required? That is called lattice enthalpy. So we can call lattice enthalpy is endothermic. Then between the Cl minus and water, attraction is possible. Due to attraction, energy is liberated. That energy is called hydration enthalpy. Hydration is exothermic. The hydration enthalpy means how much Cl minus should go for hydration means 1 mole of Cl minus. 1 mole of Cl minus ions should go for hydration. While what is the energy liberated? That is called hydration enthalpy of Cl minus. Similarly, sodium ion. So hydration enthalpy is exothermic. Now, so lattice enthalpy is we can say endothermic. Hydration enthalpy we can say exothermic. Okay. If both are equal and opposite, lattice enthalpy is equal to hydration enthalpy. Lattice enthalpy is equal to hydration enthalpy in the sense the solubility, how it will be there means normal. If lattice enthalpy is greater than hydration enthalpy, then solubility will be low because it requires energy. Net factor says endothermic. If lattice enthalpy is less than hydration enthalpy, then solubility will be more. Okay. If lattice enthalpy is less than hydration enthalpy, we can say solubility will be more. If lattice enthalpy is less than hydration enthalpy, we can say solubility will be low. If lattice enthalpy is equal to hydration enthalpy, normal. Okay. Now we will see regarding lithium fluoride. For this solubility is low. What is the reason? Now lattice enthalpy is directly proportional to charge of cation, charge of anion by radius of cation plus radius of anion. Li plus small size, size of cation is small. F minus small size, size of anion is small. Therefore lattice enthalpy is high. Therefore solubility is low. So we can say here lattice enthalpy is dominant factor. Lattice enthalpy is low. Lattice enthalpy is high here. Therefore solubility is low, we can say. Lattice enthalpy is high here. Therefore solubility is low. Then here cesium ion cation size is high. Cation size is high. I minus anion size is high. Therefore hydration tendency is low. That means hydration enthalpy is low. Hydration enthalpy is low. Therefore solubility is low. If size of cation is high, then attraction with water molecule is less. Therefore extent of hydration is less. Therefore hydration enthalpy is less. Cesium iodide solubility is low because hydration enthalpy is low. So exothermic nature is low. Therefore solubility is low. So lithium fluoride and cesium iodide. Lithium fluoride solubility is low because lattice enthalpy is high. Cesium iodide solubility is low because hydration enthalpy is low. Then lithium halides are soluble in organic solvents, ethanol, acetone, ethyl acetate, pyridine, like this, because lithium halides are having quite a covalent nature. Lithium halides are having covalent nature. Therefore lithium halides are soluble in organic solvents. Lithium halides in which lithium ion size is small, therefore covalent nature is high. Size of cation is small, in the sense covalent nature will be high. Then behavior of alkali metals in liquor ammonia. Behavior of alkali metals in liquor ammonia, we will see. In liquor ammonia, how they will behave, how alkali metals behave, that point we will see. So alkali metals we are taking a ammonia, we are taking so we are preparing what, in the sense dilute solution, otherwise concentrated solution. We will take alkali metal that will dissolve in liquid ammonia. We are getting dilute solution or concentrated solution we are getting. So now first we will see dilute solution, how dilute solution will behave. Sir, in dilute solution how the behavior will be there, that we will see. Now alkali metal will give electron and become alkali metal ion. This alkali metal ion forms complex with ammonia, like this. So this alkali metal ion forms complex with ammonia like this. This plus charge is for M. Then electron is forming complex with ammonia, that we can write like this. Electron charge is negative, that we have written. Electron is forming complex with ammonia, that is called this. This is called ammoniated electron. This name we can call ammoniated electron. Ammoniated electron, we said. This we will call it as ammoniated metal ion. Ammoniated metal ion we can call. Okay. Because of this unpaired electron, this solution is paramagnetic. This solution conducts electricity because of this electron and because of this cation. This solution is